Hi, everybody. I'm Christoph Pettis. I run a Postgres consultancy called PostgreSQL Experts. We're across the bay, that way, in Alameda. But the very first thing I want to get out of the way, the most important thing is we are having a conference. This is a community-sponsored conference in San Francisco early next year. PG Day, it's a one-day technical conference. It has a website, like all the cool kids do. It's going to be in San Francisco at the Swedish American Hall out on out on Market Street. Memberships are open. The call for papers is open. Sponsorships are open. So please buy a membership, submit a talk, and encourage your employer to sponsor. And that's the URL. So, okay, what we're going to be talking about really quickly now are things in Django and Postgres that you're probably not using that you should be. So, who has this happened to? You add a new column to a model, you create a migration, you apply the migration and realize you just added a column with a default to a 25 million row table, and the site's now down. Who has this happened to? Be honest, we're all friends here. Okay, in Postgres 11, this problem goes away. Everybody applaud. Who's on Postgres 11 in production? Who's on Postgres 12 in production? Come on, it's been out for like days now. All right, everybody out there, go just slam it into production. No one will notice. So previously in Postgres, one of the things that no one liked about Postgres is that to add a column to a table that had a default required you to rewrite the entire table. Because the Postgres, the tuple structure on disk is a fixed structure. There's no metadata in the tuple itself that says which column is which. There's only the system catalog, so it had to make space for all of this. In Postgres 11 now, when you do this addition, it makes a note in the system catalog that says this column, it has a default. So when you get it off of disk, fill in the default if it doesn't have it already. So this results in one case. If you create a new column that's nullable but has a default, you'll get the default, not null. So, and if that's a problem for you, sorry, can't make everyone happy. So it's just as fast as adding it without the default with a null column. So you no longer have to do that horrible hack of adding the column as null and then backfilling it with the default and having your code understand that none meant the default and all that stuff. Goes away forever. Yay. So upgrade to Postgres 11 already. Don't have to do anything special. No different SQL. Your migrations will just do it. So yay for that. Who has ever created an index that is not a B tree in Postgres? Who has but doesn't realize it? Okay. So one of the great new features in Django, starting in the 1.10 era, but coming up through the 2.2 era, is non-B-tree indexes. B-tree indexes are great. They do also, they slice, they dice, they make thousands of Julian fries. They're really very handy. But there are other index types in Postgres, and they're actually better for some circumstances. Who uses UUIDs for anything? Okay, B-trees kind of suck for UUIDs because they're long. You don't sort on a UUID, or if you do, you really need to reconsider your life choices that got you to that point. So building a B tree is the most general index structure possible in Postgres. So it handles total ordering, greater than or less than, or all that stuff. It doesn't care where things are on disk. It can, completely random arrangement on disk or file. But you have better choices. For example, for long types like UUIDs or text strings, a hash index is generally a superior index type. You can create those in your model now. You don't have to drop down to raw SQL to do them. Similarly, there's a relatively new index type called BRIN indexes, which is actually for block range index. A BRIN index is good for situations that have these characteristics. The field you're indexing on monotonically increases as the rows in the table were inserted. You rarely insert or update the rows, and you retrieve ranges of those. This, like time date stamps on sensor data even orders could be a very, BRIN indexes are much, much smaller than B-tree indexes. And by much smaller, replacing a multi-megabyte B-tree index could be a kilobyte size BRIN index. And because they're much smaller, they're much faster to retrieve. There's sometimes you just can't index on a B-tree sensibly, like ranges, because what does total ordering mean on a range? You know, weights in space kind of don't have greater than or less than. But they do have containment, they do have what's my closest neighbor, and things like that. GIST indexes are great for that. GIN indexes are great for things like arrays, and full text search obviously is the canonical case for them. So use those. You can go to my blog, which is thebuild.com, and there's a talk I gave recently, all time has no meaning anymore, that talks about the conditions under which you use the various Postgres indexes, so check that out. Declarative partitioning, so who's used partition tables in Postgres? Pre-version 10. Okay. Partitioning in Postgres is a way of breaking up a very large table into smaller tables on the basis of a partition key to accelerate queries on this table. It kind of always sucked. It was a hack on top of a feature that never really got fully developed in the original academic version of Postgres, back when it was called, back when it was just called Postgres without the SQL. It finally in version 10, it kind of like got all the attention it really deserved, and it became a new system called declarative partitioning. It's a much faster, it's much more easy to use to break the tables up, and the queries execute much more efficiently. It was introduced in version 10, got a huge number of improvements in both 11 and 12. So check that out. It's very, very helpful for breaking apart tables. You don't directly support it in your model. There's no way right now in the model syntax of saying, oh, by the way, partition this table for me, please, which would be kind of cool, but it was complicated for a variety of reasons. But once you do it, you don't have to fiddle with your models to make it work. It'll just work. It'll just happen in the model structure. Parallel query execution. This was a version 10 feature, one of the big version 10 features. One of the problems, Postgres isn't threaded. Every single backend, which is the process that handles your query, is single threaded. And that's true to this day. This didn't fix that problem. So if you write a big query, at any one moment there's only one I/O operation pretty much going on and only one thing happening. This is obviously not great. So in version 10, parallel query execution was added, which allowed it to fire up multiple backends to handle large queries. So for example, a very large sequential scan, could be broken up into multiple queries and processed that way. Very potentially a really huge speed improvement. So if you are doing data warehouse types of things, very large databases, very large tables, things like that, check this out. Some maintenance operations like create index can be parallelized as well. And so that's very nice. So it's enabled by default on Postgres 11 and higher. It was introduced in Postgres 10. So if you upgrade to 11 and you don't change much about your configuration, you'll just get it. So don't be too surprised when it happens. Logical replication. Okay, whoever used Slowney? Who's ever heard of Slowney? Who's scared their children by saying, if you're not good, I'll deploy Slowney to 1.x? Slowney is like the tool we all love to hate in the Postgres world. I mean, it's an amazing piece of code and it worked great, but it was a solution because we needed a solution, not because anyone thought this was the way of handling logical replication. Who's familiar with binary replication in Postgres, where you have a secondary? You know, that kind of thing. Okay. There are lots of limitations of a binary replica. You can't write to it at all. And Postgres has a very strict definition of what writing to something means, like no temporary tables and stuff like that. Query performance on it is a little weird because of conflicts with replication. I'm sure if you've run in a real life Postgres installation, you've gotten the cancel the query due to conflict with replication error message, and then called us to say, what does this mean? Logical replication works at more like the SQL level, more like it's sending the SQL queries back, the updates and the inserts over. So there are a lot of things you can do with it that you can't do with binary replication. For example, you can do a zero downtime upgrade. but you can, because unlike binary replication, you can replicate from a version 9.6 system to a version 12 system, and then just cut over to your version 12 system, which you can't do with binary replication. Binary replication, they have to be the same major version. You can, if you have secondaries that take very high query loads that would get messed up in binary replication, you can use a logical replication instead. So that's very nice. One other thing that you can't do with binary replication is replicate multiple servers onto a single server. For example, for all your front-end, OLTP systems and transactional systems, feed all that data into a single data warehouse. But you can do that with logical replication. And you can also do logical replication in Postgres is a framework. It's not a single thing. So you can take the logical replication stream and you can decode it and ship it into other stuff. Like, for example, into Kafka. Since all the cool kids use Kafka. Since LinkedIn, LinkedIn's successful. They use Kafka. Everyone has to adopt it. One thing that a very, very common thing is people turn loose a vacuum or create index, and they'll say, "How long will this take?" And we will say, "We have no idea." Why? Time has no meaning. It will run until it's done. Well, fortunately, we have better answers now, which is there are a whole flock of views that have been introduced over in versions 10, 11, and 12 to track the progress of various operations, such as vacuum and reindex, create index, and cluster for those like 5 installations out there that never use cluster. Vacuum full also gets reported with cluster. So that's much nicer, is you can have your own little monitoring tool or just log in and do a select star from the various views. There are different views for all of these, so just check out the docs and get an idea of the progress for them. This is especially nice for things like a big create index concurrently, and you're kind of wondering, so when do I get my index so my queries start working better? And again, these are all new system views. Okay, so Postgres has had constraints for a long time, since version 7.2, something like that. But using them in your Django, in Django, meant dropping down, writing custom SQL to apply the constraint, doing that sort of thing. Nothing wrong with that, but now, as of 2.2, we finally have constraints in the model. So you can just write a meta in the meta, the class meta info to create constraints. These are table level check constraints, which are constraints that check multiple columns at a time. So for example, or you can create one on a single column, of course, because previously Django didn't have a way of specifying a database level constraint. And database level constraints are nice because no matter what source the data comes in from, whether it's Django or a bulk loader or something like that, the constraint gets enforced on top of it. You can also, with table level constraints, do checks that would be impossible with just a unique constraint. One of these is the room reservation problem, where you have a range that says this room number for a hotel is booked for this date range. There's no unique constraint that can say don't have overlapping dates on the same room. But you can do that with a check constraint with the right set of indexes, so that's very nice. The fancy term in Postgres is called constraint exclusion. And that's my talk. Thank you.